Hello and welcome back to Calculus 1, section 3.7, the chain rule. This is the most used technique to find derivatives, most frequent. I would go out and say 90% of all derivatives you take from this point on in your life will be chain rule. And the most frequent and most useful technique for integration, called U substitution, will be the backwards chain rule. So in short, spend infinity of time on learning this thing and understanding it. The prerequisite knowledge that you need for this is function composition. We understand that you have basic functions, like let's say x squared or square root of x. But then you can have a square root of sine x. You can have e to the sine x. Right? You can have e to the x squared plus 3. And all of those are composite functions. They are composed from two functions using function composition. So we have to review function composition first, because you have to be able to mentally decompose functions in order to take derivatives using the formula for chain rule. So we start by relearning or whatever, reviewing function composition, denoted as f composed with g. This is a little circle here. It's not O, it's not fog. It's f circle g. We say f composed with g of x. And it means f of g of x. It means g is plugged into f. Example for this would be, say, function f of x is sine x, and function g of x is square root of x cubed plus 1. Then function f composed with g would be sine of square root of x cubed plus 1. So what we've done is we plugged in g into x of f. You know that this notation here should say f of x, and you see that x and it was replaced by g of x. We can also compute g composed with f, where we are going to keep the form of g and plug f in. Now f is sine x. So this becomes sine cubed x plus 1 in the root. So whatever the first function is, the problem is going to take shape of that function. The other function gets plugged in. Another visual that might help some of you, say f of x is equal to let's go with e to the x, and g of x, say, is, plus you need tissue? G of x equals x cubed minus 1. F composed with g, we can understand that as f of g of x, which means take f and plug g for its x. We can also have g composed with f, which is g is the boss, f gets plugged in, so this means f cubed minus 1, and that's going to be e to the x cubed minus 1. It is important that you guys can see that the structure of this technically says x cubed minus 1, and then that x is replaced with the entire g, right, or f, whatever you need to plug in. Do we see that? because this is the skill that we actually don't need. It's the backwards. It's the backwards skill that we need. It is the skill when I ask you e to the tangent x. What's f equal to? What's g equal to? That's the skill I need you to have. Backward, decomposing. So what's f? What's g? E to the x and tan x. Good. Sine squared x. What's f? What's g? Aha. Nice. Nice. How about sine x squared? Aha. Meditate on these two examples a little bit. You see, a square is not there for decoration, right? It does things. The first one up there is sine times sine. The bottom one is sine of x times x. You can see x times x here, right? This one we can rewrite as sine x everything squared. So you see how g is sine x and then everything is squared. So the main function, the outer shell of the onion, is going to be x squared, and then you replace x with sine and you get sine squared x. The bottom one, sine x, is the boss because the x was replaced by x squared. So this is the skill that you have to practice to be able to do chain rule. You have to be able to decompose functions. So cosine squared x minus 3 cosine x plus 2. F and G. Now this is the next level. This is spicy. Anyone? What happened? F? Okay, what's F? Nice. X squared minus 3x plus 2. And what's G? Cosine x. Time to stare at this for about 12 minutes. Now, if you are struggling, how about this? Something squared minus 3 times something plus 2. It's the same something. It's cosine, cosine. It's not going to work if it's cosine and sine. It has to be the same thing because it's x and x over there. Do we all see it? I said, do we all see it? Which one do you don't see? Because if you're looking here, I didn't write anything yet. Well, I rewrite this one. This is the same. So do you see how if this goes into there for that x, you get the one on the bottom, which can be written as the one on the top? Good. Now, when you go here, Sign of the argument, right? You see that square belongs to x. So if I replace this x with x squared, I get exactly right.
But if that looks like that, isn't it supposed to be sine squared x squared? Like both variables.
Aha! Somehow you know my next example. Sine to the 5th power of x squared. Sheesh. What's happening over here? But isn't that sine to the 5th also composite? Aha! We can compose as many of these as we have to looking at the application. What's the most outer layer of the onion? I don't know if you ever dealt with the onion. Anyone likes to cook other than me?
A papery outer shell.
Yeah. So onion has layers, right? What's the most outer layer for this function? X to the 5. Because I can rewrite this problem as this. So the most outer layer, you have to learn, guys, you have to learn this notation. When you see sine squared x, that is sine x squared. When you see ln squared x, that is ln x everything squared. That notation needs to be there ingrained in your head. And I'm going to actually put the box around that so you know that that's important stuff. Now, as soon as I see this 5th over here, that's the 5th for the entire problem, and that becomes the most outer layer. And then you go in, and in, and in, and in, how many times you have. So you have something to the 5th power. Something to the 5th power. There you go, something to the 5th power on the outer layer. Then I go inside, and it is sine of something. Sine of something. And then finally x squared on the bottom. Now, take this, plug it there. Then you have sine x squared. Take that, plug in here, and you have sine to the 5th x squared. Oh yeah, you take the derivative of this in 15 minutes. But if you're not able to decompose, you will not be able to set the chains correctly. You're most likely going to get the first step right, but then the rest is hell on earth if you don't know how to decompose. Sine of e to the x squared plus 3. Because we can. I could change one of the signs to cosines, but I'm not going to. How many layers do we have in this onion? 4 layers. What's the most outer layer? Very good. It's sine of something. Nice. Sine x. What's the next layer in? Again sine x. It's sine of something. Now what's the next layer? E to the x. It's e to something. And at the end, x squared plus 3. Beautiful. So these guys tend to be okay-ish, right? The ones that are a little bit evil are the one like the polynomial I had. So ln squared of x minus x ln x plus 3 over ln x. How many layers do I have here? So far I heard 4 and 5, and unfortunately none of those. Well, should I say unfortunately? I shouldn't say unfortunately, because there is a correct answer and all others are wrong. So no, not 4, not 5. Two. FG. What's G? ln x. Now if you go and you yank that ln x out of the problem, or replace this ln x with the heart, what do you get? You get heart squared minus x times heart plus 3 over heart. And I'll call that heart. Oh wait, I put x over here. Put 5. Yeah. So what do we have? X squared minus 5x plus 3 over x. Nice. Good.
So if that 5 was still x, how many functions would that work?
Yeah. Ready? The derivative of function composition is the derivative of the outer function with the composition plugged in times the derivative of the inner function. Now that's the formula and that's the end of the story. Now I will do a quick example before I explain it further. We understand that f is sine x and g is 3x to the 4 minus x squared. The derivative is the derivative of the outer function with g still plugged in. So you look over here and you say the derivative of sine is cosine, but you have to plug in g. You can't put x. So it's 3x to the 4th minus x squared times the derivative of g is 12x cubed minus 2x. Done. So observe that this is f prime of g times g prime. Meditate on this one. Why does this work? Just a quick side note. When I am taking the derivative, I take the derivative in respect to x. So the derivative of x cubed in respect to x is 3x squared minus 2 and then plus 0. Take the derivative in respect to x. Now, our formula here, f of g of x, does not have x inside the f as input. It actually has g. So, we say take the derivative of f in respect to g times take the derivative of g in respect to x. You see what happens when you cancel these two? You get the derivative of the outer function in respect to x, which is exactly what you need. So if you are trying to, understand this on the higher level, this is what happens. You are taking the derivative of f in respect to g, and that's the reason why g has to be plugged in when the derivative is done. The first derivative, right, of the first term. And then the second part is just good old derivative of g, and when they cancel, you get df dx, which is actually what we needed. So let's take the derivative of e to the x squared plus 1.
I have a quick question.
Yes.
Are we getting a formula sheet in the next test?
There will be no formula sheet ever in calculus courses on any of the calculus 1, 2, 3 differential equations. None. It's the department rule, especially Calc 2 and 3, which are just formulas, and calculations are Calc 1. That was the first argument. The more formulas, the less learning happens, and it's exponential decay in that case. So we already see any student who got any formulas in PreCalc 2, the lowest exam grade already in Calculus 2 was 9. And just following through using formulas. So it's it is not no, it's hell no. That's actually much better answer. Oh, you'll live. With a smile, just like that. Yeah, smile. What is the outer function? E to the x. What's the inner function? G. X squared plus 1. Awesome. So, what's the derivative of e to the x? So I need e to the g, right? So I get to copy the same thing. Great. Times the derivative of the g, 2x. So that's it. What? Yes.
I have a question. Like, how would you handle like cosecant? Because when you
The same. But we'll get there.
okay.
The answer is the same. Oh, I thought you were crying.
No,
What is F? Nice. What's G? Sine x. So, what's the derivative of square root of x? Nice. But you don't get to put x here, right? You get to put G. And G is sine x. Times the derivative of sine x is cosine x. So, now you can go rationalize and have fun with algebra if you want to.
Do we have to rationalize this?
No, but the issue is when this shows up in chapter 4. So, it looks like I'm determined to answer no on every of your questions, whether it's for you positive or negative outcome. Right now you are 1 for 1. Oh, sorry, you are 1 for 2, sorry. That's what I meant. In your favor. I mean, if you really don't like this, just do this question with a limit. It should take about 8 hours. Yeah, I know, right? Next question, because we can. Cosecant it is. By popular demand, we're going to do that's not cosecant. Cosecant of x squared minus 7. What's F? And what's G? All right, so what's the derivative of cosecant? No! The program exploded. So F is cosecant x, G is x squared minus 7. All right, so we said negative cosecant cotangent. Do you see how I'm setting it up? I'm not placing x's there because I know I have to plug g's in. So I have to plug in g's. And then finally times 2x. That's the chain. So this part over here is called chain. The derivative of the inside. Happy? All right, since you love tricks so much, how about the derivative of the cotangent, the square root of x? What's F? Cotangent x. What's G? Perfect. All right, let's go. So when we're done with these basic exercises, we're going to go and do the textbook exercises. And then we're going to take a look at more interesting examples after that. What we are doing right now is just scratching the surface. What should I write?
Negative cosecant squared root x times 1 over 2x.
Perfect. Perfect. So it's negative cosecant squared root x divided by 2 root x. Oh, can I cancel these square roots? Hell no. Because this root on top is the argument of cosecant. You cannot cancel. Great. I'm going to put 2 examples from the textbook for you to work on. I'll put one here and one on the board so you can see them both at the same time. I would like you to discuss these and try. I'm copying 2 exercises from the book. So these are problems 33 and 34. So here's the problem 33 done on screen. Find the derivative of secant x plus tangent x, but all of that is raised to the 5th power. No coughing. And the second example is 34. I'm going to write this on the board. I'll write it on the tablet later. The derivative of sine of 4 cosine x. They use z there, but doesn't matter. All right, go. There we go.
Where'd it go? Hunting you now.
Yeah, now we have a. Oh.
There has to be a wasp's nest, like right outside that window.
Yeah. Oh, you want the coffee? Yeah, it should be something close by. Because that's not a wasp. That's just a regular bee. By the way, it's still dangerous. If you're allergic, it takes one sometimes. Get over here. I actually got stung on Saturday. I got stung by one. Or Sunday. Right here. So I don't know if it's still there or not.
Now we're just pissing them off, though.
Yeah, I know. People usually dance.
Behind you,
stand up.
he's gonna get you.
Yeah. All right, let's focus on the derivatives. All right. Nice.
Oh, we got the brown ones.
What's the thing is actually acts as a tracer, so say one gets it, every other one knows exactly what it is.
discuss this. Three, 4, 5, 6. 12. But these are only two, so we're good. Yeah, but it's cosine. It's 4 cosine x. It's a constant. It's not, right? So let's take a look at the first one, the secant x, tan plus tangent x. So the outer function f is going to be x to the 5, and the inner function g is secant x plus tangent x. So what's the derivative? It has to be 5 times something to the 4th, and the something is the secant x plus tangent x. And then you have the derivative of secant is secant x tangent x plus secant squared x. The derivative of tangent is secant squared. Now we can do a lot of cool stuff with this. You can factor out secant on the first parenthesis. You have 5 secant x, and what's left is secant plus tangent, which makes the fifth one over here. When you factor out secant from here, what's left? Secant plus tangent. Secant plus tangent to the fourth times secant plus tangent to the first is secant plus tangent to the fifth. Right?
So you're taking out secant plus tangent.
I factor out secant, which is this one. Yes. No one asked me calculus question. I did something in algebra. Everyone goes, what? Wait, hold on. I factor out thing. That's it. And you multiply. Calculus was done here. The rest is algebra.
That's just merit on how great of a calc teacher you are and how bad our algebra teachers were.
No. I'll have to take that.
You're getting closer and closer to that statue.
So do you all see that? Do you all see the secant factored? So one secant factors out, and you are left with this. Now this and this the same, so when you multiply them, you add the exponents. 4 plus 1 is 5. Next problem is sine of 4 cosine x. F is what? Very good. What's G? Nice. Derivative of the outside. So derivative of sine is cosine of 4x for cosine x times the derivative of the other function, which is negative 4 sine x. You can't do much with this. So negative 4 sine x times cosine of 4 cosine x. There's nothing you can do with this. Because this cosine and this sine do not have the same argument. They cannot be combined. Argument is whatever goes after. When you have square root of the argument, ln of the argument, sine, cosine of the argument, that's called argument. So when I use those words. All right. Are you ready for the spicier cases?
Yes.
Okay, level 2. We have the derivative of f of g of h of x, which would be derivative of f in respect to g times the derivative of g in respect to h times the derivative of h in respect to x. And when you cancel these, you see you get derivative of f in respect to x. Great. So now I see 1, 2, 3 functions, 1, 2, 3 over here. Earlier used to be 2 and 2. What do I do if I string 8 functions? Again, yep. 1, 2, 3, 4, 5, 6, 7, 8 on this side. So the amount of functions that you have on the left is going to be equal to the amount of factors that you have on the right. All of these guys are called chains, right? That's the initial one, and these guys are called chains. So, we've seen it earlier. The derivative of sine to the 5th of x cubed. Well, f is x to the 5, g is sine x, and h is x cubed. If it's going to help, rewrite this function so you can see it easier, right? With that 5th on the parentheses around sine x cubed. And then you unleash the formula. Now, the way I think about this is I say, all right, I have something to the 5th. What is the derivative of something to the 5th? Well, it's 5 something to the 4th. What's something? Well, sine x cubed. Times the derivative of the inside. Derivative of this. Well, that's also composition, so now we have another. It's sine of something, so derivative of sine of something is cosine of that something. And finally, the derivative of something is 3x squared. Does this make sense? Let's take a look at another example that has multiple. So, how about the square root of sine of e to the x? What's f? Beautiful. What's g? Nice. What's h? The way I start the derivative is I say I have a square root of something. The derivative of square root of something is 1 over 2 square root of something. Times the derivative of the inside, which is what? Sine of something. What's the derivative of sine of something? Cosine of something, which is e to the x. And finally, what's the derivative of? Yes. And now you can make this pretty. E to the x, cosine e to the x, divided by 2 square root of sine e to the x. It's just making it pretty. Chapter 4, equal to 0. It's not going to be a problem at all. The answer is clearly ln of pi over 2. Yeah, we'll get there. What else? Well, let's see what book think it's cool. Oh, not those yet. Those are extra spicy. This is what book believes it's cool thing to do. Problem 53. Good luck. Try that one. I have to walk a little bit.
You have to do that one more, right?
What do we have? Yes? Yeah, but that's okay. You can answer too. So where do we start? What is the f? Yes, square root of x. Great. And now what's g? Very good. And what's h? We don't have it. Nice. Good. So now, the derivative of this would be 1 over 2 square root of x plus root x, right? Plus the derivative of this is what? Nice. What's the derivative of x plus square root of x? The derivative of x is 1. Oh, y plus over here. Yeah. because I'm thinking of the next step, and to be honest, I'm thinking at all. Great. So this works out to be 1 plus 1 over 2 root x divided by 2 square root of x plus root x. What now? I just leave it here? Nah, we can do better. If you can do better in life, you should. So times root x. Let's do some algebra. I know how much you love it. I don't think anyone has issue with calculus here. It's all perfect. Yeah, but this little blue thing just blows your mind, right? It's like, wow, you can actually do that? Yeah. If I multiply through, I get 2 root x plus 1. On the bottom, I have 4, which is 2 times 2. And now x multiplies these things inside, and I get x squared plus x root x. And at least now it's not a double fraction. At least. You look like you're going to cry.
I'm thinking about it.
Hold on. So now what we can do is we can rationalize this further and see how much worse we can make this. So square root of x squared plus x root x and x squared plus x root x. In the numerator, we have 2 root x plus 1 times square root of x squared plus x root x. And in the denominator, we have 4x squared plus x root x. Yeah. We made it a little bit worse. But that's okay. Right? Remember, we say equal to 0 in chapter 4. So you go figure out which, pick your poison. Equal to 0 here, equal to 0 here, equal to 0 here, or you have a fourth form that you might want to consider. It's 12 o'clock, right? On everyone's watch. 11:56. Okay, you have a more precise watch. That's good. And this class ends like 3, 4, so we have time. We're going to do spicier examples now. We've been building up to this point. Where we take product rule and quotient rule and we bring them into the mix. So you have a chain of a product, product of the chain, product of the quotient within the chain, and things like that. And the book has few exercises that you guys can enjoy, 57 through 68. That's solid 12 exercises that you guys can enjoy to practice these combinations. I'm going to make up few because I really don't want to take away from your privilege to do these things from the textbook. So let's take a look. There is always a main rule and then the other one or the next rules after that. You know PEMDAS, order of operation, right? Well, over here it's trickier. You need to see the form of the function and the function composition, and then whether it's multiplication, division, what's main thing. So tell me which one, what is the main rule for this problem? Is it the chain rule, product rule, or quotient rule? What is the main rule for this problem? Vast majority of you said product, and one person said So is it product or chain? We see product because there is this times this. But we also see a chain over here. Do you see how chain is only on the part of the problem and product is everything? Do you see that? I'm going to reverse this question now. I'm going to write it as the derivative of sine of e to the x e to the x. Do we still have a product of two functions?
Yeah.
Hell yes, we do. Right? But do you see how the entire product is embedded in sine? So over here, product, over here, chain. So you have to see these things. When you are analyzing these functions, you are clearly seeing that there is multiplication of two functions, and one of the functions is the chain rule, composition of two functions. And you realize here that chain is not the entire expression. Chain is only, the function composition is only part of the problem. This has nothing to do with function composition. This has everything to do with function composition. And it's multiplied. So product rule is the boss. The bottom problem, everything is chain, right? Everything is function composition. And then you have product inside. So chain rule is the boss. Product is something we have to do when we have to deal with the derivative. So now let's solve both of these problems. And if you pay close attention, you will see when I apply the product rule, when I apply the chain rule. So the first problem, the derivative of x squared sine x cubed, I use the product rule. Copy the first, and then derivative of the second. This is when the chain rule kicks in, because I'm taking the derivative of the function composition. The derivative of sine is cosine x cubed times 3x squared in the chain. Plus, copy the second. Times the derivative of the first, which is 2x. So this problem was chain within product. Product is the boss. Chain within the product. Now what can I factor? I can factor x. It's not worth. So when you put everything together, this becomes 3x to the fourth cosine x cubed plus 2x sine x cubed. It's really not worth factoring x and copying the whole out, everything else. I mean, you will do it in chapter 4 because you set this equal to 0 and then solve. But now we don't need to. The next, we said no coughing, right? The next part is sine of x e to the x. Now we see the function composition. It's sine of something. So we start with derivative of sine is cosine. Well, I have to go next. Derivative of sine is cosine of x e to the x. And now I have to follow with the derivative of the inside, which is the product rule. Copy the first derivative of the second plus copy the second derivative of the first. If you factor out e to the x, x plus 1, and cosine of x e to the x. Chain rule was main rule. Not good? It's good, okay. So chain rule was the main product, was embedded in chain. Now, this is new, and I understand that you haven't had practice with chain rule, so some of you might say, oh, it's hard. Once you start seeing, once you review function composition, able to decompose these things, the question is how annoying this question can get. Hard? I don't know. 2 formulas, put them together, right? But we can have a product within the chain, within the product, and all of that embedded in the quotient. It's just how annoying you want to make it. Now that we are on a topic of quotient, what is the derivative of e to the x squared divided by e to the x, let's not use e to the x again. I want e to the x plus 1. Let's just go with x cubed plus 1. What is this? Quotient rule is the boss, good. And the chain rule is whenever you have to take derivative of the numerator. All right, go on. Are we still young? All right, so denominator squared. Copy denominator as is times the derivative of the numerator, chain rule. So derivative of e to the x is e to the x, and then the derivative of the exponent, 3x squared, plus copy the top times the derivative of the bottom, 3x squared. Well, we can factor out 3x squared e to the x squared, and we are left with
on the first one in the numerator, how did we get e to the x to the third?
where?
The first e in the numerator. You get times e to the x to the
It's
third.
squared.
Okay,
Look.
so it is squared.
It is. Yeah, it is. Look.
Oh, that's what I had.
Okay, good.
Just totally erase it.
What happened?
Just totally erase it. Like 5 seconds.
I didn't see that. I don't know what he's talking about. We're on the same page here.
What was in the bottom? X cubed plus 2. Right? And then eventually chapter 4 equal to 0, and then obvious solutions, right? Like that, x equals 0 and x equals to negative, yes.
How do you get
X squared from
Experience. All right, so let's take a look at this problem together. The quotient rule formula says take denominator, square it, take denominator, put it here, derivative of the top. Derivative of the top is the chain rule, so derivative of e to the something is e to the something times the derivative of something. Ah, that's supposed to be 2x there.
That's what I
shame will be eternal?
What'd you say? I also have this. And that. And this. Oh, this is 2x over here. I copied the wrong exponent. I copied the x cubed over there, and then I took the derivative of x cubed instead of copying x squared and taking the derivative of x squared. So that's all this is going to change now. What I can factor out is x e to the x squared. So we are left with 2x cubed plus 2 plus 3x, right? Because 1x is out. Good. X e to the x squared, 2x cubed plus 3x plus 2 divided by x cubed plus 1 squared.
In the first one, over a little bit more, we got 2x plus e to the x squared. In the quotient rule, don't we subtract?
Good.
What were we doing this problem?
No, you are paying attention. I'm just testing you all. Nice. Let's pick one from the book. Ooh, before we do one from the book, okay, do that first, and then we'll deal with the one from the textbook, and then you'll have 11 left. All right, this is enough time for a problem like this. Which rule do we use? All right, let me restate the problem. Oh, come on, the pen. Why do you have to everything?
Can't handle all the excitement.
I guess. And now it won't even reconnect. Well, the screen works. It's the pen. Come on, reconnect. I hate you. So, What happened? Do it whatever way you want. What happened? Sure. There we go, the other way.
So you wouldn't use a quotient rule because technically the top's not a function?
Very good. I would never use a quotient rule for this because this is a constant. All quotient rule is too complicated to use in a case where you don't have a function there. It's a 5.
Now let's say we hypothetically looked at that saying that f is 5 over x
What do you mean?
squared, and g is sine x.
We can do that as well. What happened?
Why is the quotient rule complicated? I know that the derivative of 1 over x is negative 1 over x squared. You can use that rule here.
That was not quotient rule. It's a basic derivative.
It's like quotient rule.
It's actually chain rule. So quotient rule is the only useless rule that we have, and generally no one remembers it past the past the chain rule, because when you write the quotient rule, which is the derivative of u over v, it's actually the derivative of u times v to the minus 1. So it's a product rule with a chain here. So quotient rule is something that people remember for convenience so they don't have to mess with the product rule and chain at the same time. But it is really overkill to use if you have the derivative of, let's say, 3 over x plus 6. If you have this situation, you should never, ever, ever use quotient rule on it, because this is a clear chain rule question. This immediately rewrites as 3 times x plus 6 to the negative 1, and then just use the basic chain rule. It's negative 3 x plus 6 to the negative 2. The derivative of the inside is 1, so no one cares about that. Becomes negative 3 over x plus 6 squared. So there is no need to invoke quotient rule ever, actually, but we do because it's more convenient than product and chain together on the problems that are complicated. Now this problem here just has 3, right? If that was 3x, well, no big deal. Just do the product rule between these two things. Start at 3x. Use the product rule. It's not the end of the world, but you might want to use quotient rule if you have 3x, because it will be shorter. But if you have the just a number there, it's much faster to use just a chain rule and be done with it. Because this is not going to be a product rule here. It's not 3x, it's 3. Does that answer your question?
Maybe.
Because you were asking me to put 3x over there.
Yeah.
Good. So one more problem and then cool off before the last section. Or you have enough examples and chain rule is now just no problem. Pick one. One more problem or break? One more. There we go.
But what I'm looking at is your second one. The first, you don't hit. You don't hit the derivative. Yeah, EDX is a bad example. EDX derivative. EDX no. Because your G here was signed to X. That's why you changed it. But if you go back, if you go back here, your G is the 8, so you would apply 7 or 8 sine X to the 7. And then for this one, you apply the you gotta, in this equation, in this example, your sine X is your second value. That's why you're converting it there, but you still wouldn't convert this in this step.
For the X sine X, you just do for the next one.
I mean, here, yeah, you just plug in this. So if this was anything else, like X squared, you would do that.
What should we do here? Where do we start?
I got 1. Or do you want overall what we got, or steps?
No, what would you do first when you see a problem like this? What would be the most?
Broke it down for the composition.
Broke it down in compositions. How many functions would that be? 3. Root x and then
X to the 8 and sine X. Flip.
yeah, sine x and then x to the no, x squared and then sine x. Sine x is the last. So root x, x to the 8, sine x. Or
Wait, hold on, go back. What was the order? Root x.
root x, x to the 8, sine x.
Yeah,
That's what you said?
yeah.
Okay. Then you're correct. So root x, x to the 8 on sine x. Or, oh, she's busy on the phone now. Sine to the 4th power, exactly. And that. Because square root of 8 is 4. You get the same thing. What do you mean it's the same thing? You better be the same thing. Otherwise the world would cave in. And yeah. If you do it a long way, it would be 1 over 2 square root of sine 8 to the x, and then you have 8 sine to the 7 x cosine x. And then these guys would cancel down to sine to the 4th, and then this and this would cancel to sine on the 3rd, which is what we have, and there you go. And 8 divided by 2 is 4. It has to work. It's mathematics. All right. Great. Well, that's the chain rule. We're going to take 2 minutes, and then implicit differentiation. You're going to love it. Bye.